where is this all coming from? Well, it's just going straight back to the conditional probability chain rule that we've already reviewed. I'm just going to write this out in kind of a standard form here, which is that for some set of random variables, by the chain rule, we can always expand that joint probability of the set of all of those random variables as the product of conditional probabilities of the form where one of our variables is the subject of a conditional probability term, and basically we have in the condition a successively larger and larger number of other random variables, basically the ones that have already been taken into account as the subject of a preceding conditional probability term. So what does that look like? It looks like one simple way to expand it would be probability of x1, x2 on up to xn equals probability of x1 unconditional times probability of x2 given x1 times probability of x3 given x1 and x2 on out to probability of xn given x1 through xn minus 1. Okay? So that's pretty much the same thing that you've already heard. We're just now being explicit about it applying to any number of variables. This is always true. It's just basically almost like the definition of conditional probability and joint probability. They're connected together in this way. Note that joint probability is symmetric. It's equivalent to exchange of any of these variables, right? So we can do this expansion in any order we want. So the joint probability chain rule, this general form, has sort of a combinatorial number of possible expansions. You can start with x1, or you can start with xn, or you can start with x77. Whatever you want to start with as the variable that's whose probability is not conditioned on anything else. You get to do that. It's up to you. So that's the general, fully general chain rule. Always true that you can expand the joint probability in that way.